So it's 10 o'clock. We wait for one more minute. There's still participants joining. So I think we can start. With an Austrian Servus, we would like to welcome all participants from around the world to this webinar of Thomas Schutzbarton about design and verification for slope stability. A special welcome also to our competitors who are interested in what we are doing. My name is Markus Heiden. I'm a mountain risk engineer and responsible for international sales at Troma. Together with me is my colleague, Dr. Axel Volkwein from our Research and Development Department. And he will introduce us the new online design and verification tool, TheSlopeStaysHere. So let's start. Axel, what is this webinar about? Can you give us a brief introduction, please?
Thank you, Markus, for the introduction. I think every participant in this webinar knows that an unstable steep slope can be secured by nails and flexible facings. Very often we can see the stabilization works also with shot concrete on the slope. But in our case, we are using the steel mesh. This is much more favorable in terms of greening, water flows, and it's also a very sustainable way in the slope protection. So if we have, we can see here some example pictures. Here, if we are facing of a rock face, here it's a more grassy slope that has to be protected. Another example also here, more a rocky face. And what you can see that these installations are usually a combination of a mesh and some anchor plates that are connected to the nails that go into the ground. So and this is a system. So we need a combination of a mesh and certain plates that interact together and that guarantee that everything is stable. The mesh itself is delivered on rolls. They have dimensions with lengths up to 30 meters and widths of up to 4 meters. So you can also have smaller rolls, but usually these are the typical sizes of the system. To secure the mesh also at the borders or edges of the slope, we combine our plates with certain mesh ropes, steel ropes, that keep the mesh on the slope. The question is, so we are using a product that is a civil engineering product or for civil protection, and there is now a guideline that defines how we have to test and to study or design these meshes. This guideline came out in June 2016, but the origins of this guideline are much older. It was in 2000, that means almost a quarter of a century, so 24 years ago, there were two civil engineers from Switzerland, and the guys were called Rücker and Flum, and they developed a calculation method to design these mesh facings along a slope. And based on these calculations, this European standard came out in 2016. So this guideline, you can download it for free from the internet, describes what are these products for. For example, here's an example picture from this guideline. So we have the slope protection. And it also shows what details of a system have to be assessed in terms of for an official assessment or CE certificate by the European Union. We have some geometrical values. This is the numbers of meshes and transfer and longitudinal directions. We have the mesh widths, the height, so clearance of the mesh, so what size of particles can go through it. And then we have also in the section 3 in this table, there are relevant values on the strength of the mesh. And we will see afterwards in the webinar a little bit more on these values here. So this means how strong can I push on the mesh that it doesn't break through the anchor plate, for example. To calculate, to do it now, analysis with these values, there's some commercial software available like Geo5 or the GGU Stability. They have already implemented an interface to consider these meshings on the slope. But I think not everybody has a license for these two programs, and many other people are using different software packages like Larix or the things from Geoscience that provide all kinds of proofs for the groundworks, but doesn't have a special tool for the consideration of mesh facings. And to help these people, we created this free online tool for the design of mesh facings. We call it "The Slope Stays Here," so meaning we don't let the slope go down. And the thing is, this web page is an open site, so everybody can use it. You don't need any login. And the site just uses the calculation method that has been introduced by these Swiss engineers 24 years ago. And I think it's a good solution in combination if you use this tool with mesh systems that have a valid certification through the EU. We will go later on into this tool. Maybe we can, it's very famous to use mesh facings on the slope that have are made of high strength steel, but this tool also considers standard meshes that are available in different strengths on the market. So far, so good, Markus?
Yes, okay, I see. Are there any other advantages of this tool?
Yes, I think it is the idea that the planner can use it and to have all the proofs that are necessary for a stable design of the slope are integrated here. So he doesn't have to take care on how to exactly calculate it because the tool does it for him or her. And as is conformed with current standards, has a very simple input, and in the end, you can create a PDF report that you directly can put to the documents that you need to prove the stability of the soil. And the other thing is, you also can play around with the distance of the single soil nails, so you can reduce or optimize the drilling costs.
Mm-hmm. Okay.
I think we can go into the tool and have a look to it, if it's fine for you.
Yeah, sure. There are one more question.
Yes.
One more question. So why do we need all these proofs for, let's say there's a slope without any failure it's stable, the forces are balanced. So why should we apply a mesh and nails on top of it?
Very, very good. Yeah. In principle, you're fully right. So the slope might be stable right for the moment. So we created a slope, or we have a natural slope, or we did some excavation works.
Mhm.
But for example, if something changes in the future, so you have an additional load on top of the slope, you do some excavations at the toe of the slope, you get some vibrations induced, or you have other dynamic loads like an earthquake, then the slope might fail. And same situation is faced in case that we have some water in the slope. So the water loosens the cohesion and my groundwater flow or rain, and that might loosen the soil. So you need the stability.
Mhm.
And then there's another issue. Maybe the slope is stable right now, but you have no reserves. And I think all the standards around the globe demand a safety factor and for these constructions. So the mesh increases the safety of the slope. So it's more or less a safety factor.
Okay, okay. This was important to mention, I think. Coming back to the tool, can we explain now step by step how it exactly works?
Yes, of course. Yeah.
Very good.
So um, we are right here on the web page. The slope stays here. I hope everybody can see this. And um, we have it's to split screen. So if I zoom in, the design sometimes changes to one column, but it works right now. You get a short introduction on the left-hand side. And if you run the tool for the first time, you have to acknowledge a disclaimer because Truma, of course, cannot be responsible for everything. So everybody must be aware what he's using it for. In the tool, if I hide these information details, you find on the left-hand side some information, and this is a dynamic part. So we are still in a beta version, you can see here. And if we realize that the users have some questions or some details are not clear enough yet, so this help line will be extended in the future. The tool itself allows to change languages to different languages fitting for your needs. We are in an English webinar today, so we stay with English. And in the beginning, we thought of having everything on one long web page, but that would mean to have a lot of scrolling around. And so we decided to put it in different chapters or sections. And in the first 4 sections, we are doing the input data. And in the sections 5 and 6, we get all the proofs that you want to have. Let's start with the geometry. So we have a slope here, and we have an unstable layer. We have a cross-section of the nails with the spike plate, and the mesh is on top. On the right-hand side, you see a typical grid. So what we foresee is that we have rows of nails, and the nails are shifted from one row to the next one. So we create like encapsulated areas limited to the left and the right and top and the bottom by single nails. This is the main idea of the installation, and this is foreseen like that by the European guideline. In the tool, you find here always some nice circles, and these give you more information on the values you have to enter. So you, for example, a valid range. And it also states later on which formula is used to calculate these values in case someone wants to have more details. So what we enter here, we have the slope inclination. Let's say we go for 60 degrees. That's just a preset value. We can also make it steeper. Let's go for 70 degrees. we have an horizontal nail distance. Let's stay with 2 meters, but the vertical nail distance we want to increase, for example, for 3 meters. Maybe not 23, so 3 meters better. Oh, sorry, there was the comma missing. No, 3 meters. So you can see if I enter an invalid value, it turns red and tells you that you have to correct it. The nails usually are installed with a certain inclination to the horizontal, because then the injection material can stay safe in the borehole. Make it some more flat, 15 degrees. And then very important, we have a layer thickness. In many cases, we realize that the clients always say we have 1 meter, but sometimes you have higher one, 1.3 meters. We have here a point there's predefined. There's the upper width of anchor plate's pressure cone. So we have here an anchor plate, and if we span the anchor, or if we pressure the anchor plate on this cone here, we get the pressure into the ground, and we have a certain width of the plate. And this value will be taken automatically from the system you choose later on. We have a propagation angle of the pressure cone. In many cases, this is 45 degrees, but we can also say maybe we have this pressure cone is not widening this much, so we only go for 40 degrees. And then very important for the soil, we have a characteristic friction angle, meaning you have different material, you get a certain friction angle. In this case, we just stay with 30 degrees, for example. And then another important point for the ground is the cohesion. Of course, if I have some cohesion in the ground, it gives more stability of the slope itself. I personally like it more to keep it on 0. So the worst case for the slope is if there's no cohesion. So I'm always on the safe side. And of course, we have a certain characteristic density of the material. The density here is not given in kilogram per cubic meter, but in kilonewton per cubic meter.
Axel, can you zoom in a little bit so we can easier see that? I think it's a little bit too small. Yeah, perfect.
All right.
Thank you.
This must be. So, okay. At the end of every chapter, you find a red reset button. If you reset it, everything, all the values you entered will go to the predefined ones. We don't want to do it right now. We just say save and proceed. And then the tool just jumps to the next chapter. And here's here can you choose the material you want to put on the slope. So you have kind of a catalog here. One mesh is called Sigma. We have HPN, HPN plus, and then we have rectangular nettings. So these are nettings made from normal steel. You can it's not a high strength steel. And depending on which system you chose, these characteristic stability values that I showed you in the table of the European guideline are selected automatically. So if I change to Sigma, I get different values here. And if I change to HPM plus, I get also other values. These are chosen automatically. We are working on a version where you also can enter your own values in case you have different combination of material. Will be a task for the next weeks. And also you have a kind of a catalog for the different nails that are available usually on the market. And also this catalog will get an own section where you can enter your own values. You can also choose if you want to consider corrosion losses. So if you unmark this, the strength values of the nails change accordingly. Save and proceed to the next chapter. And here we come to the section where what we need the mesh for. These are additional load cases that can happen. One is, for example, if I have to consider an earthquake. So the earthquakes give an additional acceleration to the slope, and this additional acceleration or loads have been taken by the mesh. Here are predefined values. The Eurocode 8 defines, for example, in horizontal direction an acceleration of 0.175 and in vertical direction of 0.085. Maybe we don't have, we have to consider earthquake, but we don't have to consider some slope parallel flow. It's a very dry area. We don't expect very water flow, so we can unmark this one here. Now save and proceed. And now we come to the main part for every design engineer. These are the safety factors. And here we have some information on the top, how the systems work. So for example, if I go into the Eurocode C7, the standard for geotechnics, there's written that the safety factor for friction angle is put 1.0. The safety factor for cohesion is to put to 1.0, and the safety factor of density is to be set to 1.35. We also have like the so-called consequent classes that define which resistance safety factor or which safety factor on the resistance side we have to consider. And they give, for example, values of 1.4 and 1.6. In the past, it also has been, there was a model uncertainty factor introduced because it's still a mechanical model we use to design the slope. But if you trust the model very much, you can set this also to 1.0. So you have no additional safety. What we realized in the past that these safety factors very seldom have been used like this as given by the Eurocode, but the people just use the safety factor for the friction angle and no safety factor for the density. This is up to you. You have to show, and this is what an engineer still has to do, which standard he has to use and which safety factor to enter. We have now an example here. For example, no safety factor for the friction angle. Partial factor for the cohesion is also 0, but our cohesion was 0 anyway, so stays 0. And we have a safety factor for the density as given by the Eurocode for 1.35. Resistance coefficient taken for the consequent class 1.1 and 2 is set to 1.4. And for the nails, in this case, we also choose 1.4. Partial safety factor of the model uncertainty we can also keep with 1.1. And now it's the point, we had entered everything, and now the tool has to calculate the loads that are given by a sliding body that pushes on the mesh at the lower part of one row.
But one question from my side. But how do you know the geometry of this sliding block? This is
oh yeah, thank you very much. Very good point. You're fully right. We have one nail row, for example, up here, and we have another nail row down here, and this part in between forms a sliding body. And it's not necessary that the whole depth of the unstable layer is accelerated. Maybe it's only the upper half, and also this angle beta might change. We don't know. Maybe it's like large like this, and we have the whole part here. We don't know yet. And so the exact geometry, every single setup could create different forces that are pushing down here on the mesh. So, and this is the reason why we have a computer, because the computer does 1,500 simulations in the background to see which sliding body produces the highest load.
Mhm.
Thank you for this question.
Yeah, that was very good to answer.
All right, yeah, and this is the point where we come to the calculation itself. So we had the sliding body, and we had the sections up to chapters 4 covered, and now we have 2 remaining sections, 5 and 6, where all the proofs are done. Maybe I zoom a little bit out again. So you find here proof 1 and 2, and you find here proofs 3, 4, 5. Yeah,
Wow.
that is done by computer.
There's quite a lot of verifications, quite a lot of proofs. So do we need all of them? And maybe you can explain a little one by one.
Yes, you're right. Of course, these are the proofs that were developed by the Swiss engineers some years ago,
Mhm.
and um, you there are different modes of failure. This installation can happen. So, for example, if there's too much tension on the surface of the mesh might fail because there's too much tension at the upper nail. The mesh can be pushed through, or the anchor plate can be pushed through the mesh, and then the whole everything fails. So the different combination for the mesh, for the plate in combination with the mesh, and for the nails itself have to be proven separately.
I have
Maybe,
seen,
yeah.
sorry to interrupt you. I have seen there's quite a lot questions now. You can, everyone who can actually write questions in the Q&A of this webinar. And at the end of this webinar, there will be time to answer some questions. So just to mention it for our participants that they can raise any questions and we will answer some of them later on.
Yes, of course. We are and always also keen on feedback. This is the beta version. You can give us always a feedback using this mail address up here, so we can improve this tool for the future. The first proof, we won't go into the details of all these single
Sure.
formulas. You can study them afterwards. We also gave if you have here these show details, we have 2 references you can find on the internet here, where you can get all the theory also in a written form. But also you can contact us to get this information directly from us. The first proof that says, okay, I have a certain amount of tension that pulls the mesh downward based on pulling on the upper nail. And now it's interesting, the design approach says this force has never been measured in the field somehow. So we just assume a value. And then we prove that our assumption is smaller than the maximum resistance of the system. This is kind of strange, we know, but this is a method that works now for 22 years and seems everybody to accept it. You find here in the brackets the maximum value you can enter. For example, if I go to 23, which is higher than the value, it doesn't accept it. It turns to red. So we have to stay below the maximum value. This maximum value is clearly chosen that it works with the resistance and the given safety factor. So this proof 1 is fulfilled with 69% because we chose a very high value. Really, it sounds strange. We have to assume value and to show that our assumption is right, but this is the procedure given by the European guideline. The next proof, and this is the main proof, it shows or it calculates that the load that comes to the lower spike plate is low enough that the mesh is not pushed, or that the anchor plate is not pushed through the mesh. And this is the value, or the way where in the background we calculate a lot of, or 1,500 combinations. And you can see here we entered an unstable layer thickness of 1.3 meters, and the critical value is 0.59 meters. We get a beta angle of 57 degrees. And for these values, we get a maximum force that is the soil pushing the anchor plate through the mesh. We have the resistance side, and we have a safety factor. And then we see that we have this proof also fulfilled, and we use 47% of the capacity of our system. So we now can increase the nail distance to go to the top to have this proof just solved by almost 1. So far, so good, Markus.
Oh yeah, sounds very reasonable. I've seen there is one alternative proof right here below.
Yes.
What does it mean?
Yeah, you're right. What you realized that up here for the proof 1, you have to assume a value for Z. Nobody has ever measured it or calculated it. So we try to get rid of this assumption, and we call it alternative proof because it's an enhancement to the existing ones given by the guideline. The idea is, so if I increase the Z value, then I get a smaller p-value. And now is the question, what happens if I assume Z to 0, that it's a very small one? Would the mesh then still be able to retain the load coming for the p load? And if so, then I don't need further proofs. Then I don't have to assume any Z value. So you can see, yes, the system is capable to retain this value. So I have here 0 for Z and a maximum value for PD. Only if I would have the proof 2 very close to 1, then probably I will need a Z value. We can have a short try. For example, let's make the nail distance much larger. So we go for horizontal nail distance, for example, for 4 meters. Let's see what happens then. Maybe it's too strong and the proof won't work. Oh no, now we are too strong. We have too much load. And also the alternative proof doesn't work. But what you can see here now, if the system realizes I have a very high PD, then the system automatically chooses the maximum Z value, which is 22.9, we just saw it before, and tries whether the proof then works. And this is the difference here. So the proof 2 is not so fulfilled by 210%, so we have too much load on it. And the Z value reduces the load a little bit. Not very much, but it tries to reduce it. So for the engineer to use it, you can go with proofs 1 and 2. This is according to the guideline. But when you're lazy, and maybe the future brings us that these alternative proofs are also valid for the officials, then you can just go with the alternative ones and ignore the upper ones.
Okay, seems not easy, but maybe we will need some more time to fully understand and practice the tool. use it more often.
Yeah.
Maybe there will be some more questions in the future also from our participants. So can they contact us on questions? You mentioned you have an email in the tool where they can send us some questions, right?
Exactly. And also after this webinar, maybe we go quickly through the last section with the other proofs. We won't go into detail. I think it takes too long. We now could adjust, for example, the distances between the nails, or we choose a different system as a whole to fulfill all the proofs. For example, if you go to system and we now choose these, maybe let's take Sigma and see what happens, whether other proofs are then solved or not. Most probably you will have to reduce the anchor distance. Yes, we are a little bit better now, but not fully enough. But just let me show the final proofs. So we have here the proofs that are relevant for the nail. So I push, when I install the system, I push the anchor plate with a screw on the slope and push it into the ground and apply a certain pretension. This pretension is also to be chosen by the user. So typical values are 1 ton per nail, for example, which is about 10 kilonewtons. Here's this 1.5 tons. We give kind of a hint what is the maximum value for this pretensioning. And this is given by the bending stiffness of the steel plate. So if I push the plate too much into the ground, then the plate will bend over. So we say, yeah, keep this pretensioning below the maximum value, and then you can calculate it. Of course, this pretensioning needs other safety factors in terms of it has some positive effects and negative effects. So you can have a relieving safety factor of 0.8 and then load resistance one we chose for 1.4 as we did before. So if you click on the images, they will also enlarge. So we get here the proofs. So this is the sliding of a superficial layer parallel to the slope. That means the nail has to suffer a certain shear load, and this would be then the proof for the shear load. And we have next proof is the combination against puncturing, so that if I pretension the system too high and I get the load by the soil, then I have to prove that everything works. This is luckily a good one in this case. And for the final choice, we have to prove the single nails. And there's important that we have different combinations, which is shear and pretensioning, and we have the shear and the pushing load. So the formulas are written here in the side for the proofs. Doesn't look very nice if everything is such red. Let's change a stronger nail and maybe make the distance between the nails smaller. There's nothing red anymore. Perfect. And so in the end, we get a proof for the nails that are very good used, 89%, 98%. And then we get also the tension load for the nails. That this load you can use to design your nails and also nail length in the ground. So far, all the proofs.
Right. So all these verifications seem to rely on one unstable layer, the top layer of the slope surface. So what about the global stability? Is it also considered?
Very, very important point, because we really stay with a superficial slope protection. We don't go into the ground because we don't know the situation in the depth. So for these, the engineers have to use standard geotechnical software or calculation schemes to prove the global stability. It's also written down here. We have no consideration of the global stability. It can be that the global proof of the global stability requires thicker nails and especially most probably longer nails to retain everything. So keep this in mind when using the tool. There's no proof of the global stability of the slope.
I see. Axel, to be honest, some of us have already used different tools like this called Rovolum. Isn't the slope stays here the same?
Yeah, in principle, you're right. It's just a different surface or user interface you can use because the calculation schemes are exactly the same. They were invented in 2000, and since then you can use it. It was our idea to have an open access tool and to provide as much transparency and traceability of the individual calculation steps as possible.
Very good, very good. Yeah, many thanks, Axel, for the introduction of the TheSlopeStaysHere. I think there will be a lot of participants start using it now and in the future. Last but not least, we also want to mention that you can also use our online tool, the Rock Stops here, where you can design and verify your rockfall protection barriers according to the Austrian guideline. And do we have time for some questions, Axel?
Yes, of course. So the questions could happen right now. You also another possibility is to get in contact with our colleagues. For example, if you go to the webpage of Trümmerschutzbauten, if you have the contacts for the different countries, like in Germany, Switzerland, North South America, and also you can choose here the country where you're working in, and then you get an email address that directly so you can directly reach the right person.
All right.
But if you have questions now, I'm
yes,
fully open.
I will pick some questions. Can you switch back to the PowerPoint presentation, Axel?
Yes.
So now, what are the questions? A very common question is, what is the definition of the thickness of the unstable layers on the slopes for which the tool can be used, and how large can it be? So the definition
Okay.
basically
Yes.
on the surface layer.
So if you go into the tool back to the input data and we enlarge this picture, you see here this unstable layer thickness is measured orthogonally to the slope inclination. So you can drill it through the ground until you reach the rock underneath, and the length of your hole gives you the thickness here. Theoretically, T can be anything. We, in our tool, so far limited it to 2 meters. But if the experience shows that people want to have to cover also larger depths, then we might increase this valued value.
Very good. One more question. The tool always mentions soil. What about rock faces, hard rock or similar? Can we apply it?
Yes, why not? Because usually, if you have a sliding body of the soil, we handle it as a single mass in the code. We don't handle it as brittle code or small particle that form, but we keep it as a rigid body. And this would be the same for rock material. It's another point that rock material that needs a facing usually is already very brittle, or the erosion is quite strong. So we don't expect, you usually don't expect large blocks to be activated. So it works for the rocks as well. We are preparing an alternative proof for the future that is focusing only on rocks, but so far you can use it for both. And it has been shown in the past more than 20 years that the calculation scheme works for both applications.
Okay, thanks. One more question. There is one question about how we can order material directly out of the tool, because some users maybe know this from our TheSlopeStaysHere tool, where you can submit your order or your request, basically. Can we also do it here, that they do the verification and then click on the button and we receive the request for an offer?
I see, yeah. We created this webpage more as a design tool. It's not like a sales tool itself. So you do you can choose a system, of course, but for the order, there are so many other informations needed, like what is the location of the project, how to reach it, how to deliver material, what is the area you have to cover. So there are a lot of details specific for a single project that have to be clarified in advance before you order anything. So I think it's still the best then to contact our colleagues to get these details or to handle these details with them.
All right, all right. We have prepared one more slide, Axel, where they find all the information about other webinars which will follow. Maybe we can show that at the end. There will be more webinars in the future, also in German and at a different time. And I think one final question, can I get information on necessary nail lengths? You mentioned this in the verification, I guess.
Yes. It's a very, very last part of the tool. So go to part 6. We have here, we calculate the tension load that can in maximum act on one single nail. And then you can enter a certain skin friction. So if you drill into the ground with, for example, 90 millimeter holes, and you know the skin friction along the borehole per running meter, then the tool gives us, for example, possible nail length. In this case, we have very high loads, so you would need to drill for 25 meters into the ground. This is not a realistic example.
The skin friction is also very low here, I think.
Exactly.
Yeah.
So as soon as we go to good rock face values, then we end up in much more reasonable lengths here.
Yes. Yeah.
And this length calculation takes in account the anchoring length in the stable ground, plus the anchor length in the slope soil layer.
Okay, thank you very much. I think we will end it here. If there are more questions, I think everybody knows how to contact us. We are happy to receive feedback on this tool or ideas for other additional applications. Thank you, Axel, for the introduction. It was very interesting also for me to see it step by step. And yeah, looking forward to the next webinars.
Thank you from my side as well for this kind exchange, and I hope all the listeners enjoyed it. And so if you have any questions and suggestions, please don't hesitate to tell us. Thank you.
Thank you. Thank you, everyone. Have a good day. Have a good night. Have a good morning around the world.